Section 3 here is all about temperature. And we talked about it a little bit when we got into measuring scales, but here it describes it as a measure of how hot or cold something is compared to another object. And that works as a description. In reality, when we measure a temperature, we are measuring the average kinetic energy of a substance. Kinetic energy is the energy of motion. We'll actually get into energy here in this topic. If you're not familiar with energy, it's coming up in this chapter. But the average is some particles are going to be moving fast and some particles are going to be moving slow. But if we're talking a solid, most of them are vibrating. It's just that some might be vibrating faster than the others. Well, the temperature is an average of how fast all of them are vibrating. And we do that by using the thermometer. And usually what happens is, technically speaking, the thermometer is reaching the same temperature as the surroundings, and then it's reading its own temperature. But there we go. In science, I would say in the metric system, we use degrees Celsius or Kelvin. And Kelvin is coming up here in this topic. So here we go. There are different temperature scales: Fahrenheit, which we label as degrees F; Celsius, which we label as degrees C; Kelvin, which we just label as K. There's a reason why it's degrees on one and not on the other. You don't have to worry about it. But what it is, it turns out, is that there is an absolute minimum temperature we can hit. And so since there's an absolute coldest something can get, rather than having that be a negative number, and it's around negative 460 on Fahrenheit, don't quote me on that because I don't have it memorized. It's negative 273 on the Celsius scale. There's some decimals there, but that's good enough for our purposes. But on the Kelvin scale, it makes sense to call that coldest temperature you can get 0. Well, if it's 0, then we count up from there. No other measurement scale we have goes negative, really. I mean, you don't measure a negative length of an object. You just measure its length, and it's so many centimeters or whatever your preferred unit is there. And so it doesn't make a lot of sense to have a negative temperature scale that can go into negative numbers. And so then we adjust accordingly. I think I mentioned this back when we were covering units, but Celsius scale and much of the metric system is based off of water. The Fahrenheit scale, the goal was to have 0 be the coldest temperature he could achieve at the time, which I know this is in boiling water, that's not 0, but if we were to continue the scale on the thermometer, 0 is down this way somewhere. I'm not the scale, obviously, but let's say 0's there-ish, fine. Anyway, his goal was, Mr. Fahrenheit's goal was to have the human body temperature be at 100, and he thought that water boiled at 200. Well, he sets his temperature scale and he sets the spacing on it to be, yay big, whatever that is on his temperature scale, on, this or that thermometer. Well, when we made more precise thermometers, you adjust the scale as necessary to match, but we picked the known temperatures and then we start gauging things. Well, it turns out that he was slightly off. So this one's slightly higher, this one's ever so slightly lower, and the freezing point of water is an afterthought. It was just something he could measure with it, and the idea that he couldn't get a colder temperature, I mean, this was the coldest temperature you could produce artificially. Now we can produce even colder temperatures artificially, and not only that, but nature produces temperatures below 0 Fahrenheit all the time. So it was kind of nonsensical as a scale, and you maybe like it but you've been forced to memorize weird numbers your whole life with it. With the metric system, just like all the other things, it's tens. So we have a 0 here, we have 100 here, that's just 10 times 10, but it was the freezing and boiling point of water that were set as that. 100 degrees Celsius matches 100 degrees Kelvin, and so the spacing on the Kelvin scale matches the spacing on the Celsius scale. We just have the numbering be different. There is a English equivalent called the Rankine scale. I think I'm spelling that right. It uses R. It's pretty much used nowhere, but it does exist, and it's a scale where 0 is down here, and then the spacing is the same as the Fahrenheit scale. I want to point out here as well that we have 180 degrees here is our difference, and that's going to come up in our formula that we learn here in this section to convert one to the other. In fact, here it is. That 1.8 degrees Fahrenheit is equal to 1 degree Celsius. And that means that this one here can almost be used as a conversion factor. It's not quite perfect, though, because 0 isn't at the same place. For something like a meter stick or a graduated cylinder, 0 inches and 0 centimeters are at the same location. And so then we can have a conversion factor that just works like this. Because their zeros aren't at the same point, there's a shift that has to happen. And so we'll see that here in a moment when we get to going over those formulas. Anyway, wouldn't it hurt to know the actual transition temperatures of water? But the temperature at which water freezes is 0 degrees Celsius. On the Kelvin scale, it's 273. On the Fahrenheit scale, it's 32 degrees Fahrenheit, but that makes our answer number 2 there. Temperature at which water boils, let's see, that would be this one here on the Kelvin scale. For the Fahrenheit, it's 212 degrees Fahrenheit, and for the Celsius scale, it is 100 degrees Celsius. They didn't give us a Celsius choice here. And then Celsius units between boiling and freezing, that is 100 units. That's also true on the Kelvin scale. This is what it is on the Fahrenheit scale, but isn't our answer for this one. And this here just is an unrelated number. So to convert between temperature scales here, if we want to figure out the Fahrenheit temperature from a Celsius temperature, we take the Celsius temperature, we multiply it by 1.8, and then we have to add 32 to it. And this here is the conversion factor thing. So if we have a temperature in degrees Celsius, we can do the conversion factor thing where it is 1.8 degrees Fahrenheit to 1 degree Celsius, and we can cancel out our units there. And that gives us the approximate, let's call it, degrees Fahrenheit. However, because there's 0 points don't match, the Celsius scale for water is freezes at 0. For the Fahrenheit scale, it freezes at 32. We then have to do that 32 degree adjustment. And so there's an adjustment for the freezing point. If you want to jot it down, this is the formula for solving for Celsius. Instead, personally, I take this one and I use basic algebra to rearrange it instead every time. I also have kind of just memorized, at some point I had a teacher who made me do it, but I've kind of memorized that the Fahrenheit scale, the numbers are bigger. That is, we go from 32 to 212 for water, for example, whereas on the Celsius scale, we go from 0 to 100. So the Fahrenheit numbers are bigger. And so if I want to go from Celsius to Fahrenheit, I multiply by that 1.8. And then I can remember these two related to one another, the freezing point of water. And okay, once I multiply, then I have to add that 32. For the reverse process here, you'll notice that we subtract 32 and then divide by 1.8. For me, I remember it because the going from Fahrenheit to Celsius, the numbers are getting smaller. And so to make them smaller, I have to divide. And then again, I'm going from Fahrenheit to Celsius, and so I need to get rid of that extra 32. So that's kind of how I do it, rather than having two formulas written down. Rearranging algebraically works, or kind of thinking through it. Having said that, for thinking through it, I've memorized both the multiply and divide by 1.8, and then having to do the 32 adjustment afterwards. But I literally think through it like that. I don't have the exact formula memorized. I just think, okay, do I need to be bigger or smaller? Multiply or divide, and then which way am I going? Do I need to add or subtract that 32? I will also say you'll see some places that will use 9/5, and they'll say multiply by 9/5 going one way, or multiply by 5/9 going the other way, and that's what the this here is your 9/5 multiply. Rather than doing this divide, they'll take that fraction and they'll flip it, and they'll do 5/9. But you still have to subtract the 32 instead. To me, that one's always confused me. I can work it out once I think of what the 1.8 is, but it's ugly. But just in case you see it somewhere, you have another way that you can go about using this, using the 1.8, which is just much easier. Anyway, typical room temperature is around 21 degrees Celsius. What is that in Fahrenheit? So using the formula that they gave you, the temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus 32. So that's 1.8 times 21 plus 32, and that's going to give me 70 degrees. Now, I don't have that memorized. I have a note over here on the side where I've worked this out because I punched it into a calculator previously. But if you punch it into a calculator, you'll see that this is what you get. As a side note, 2 sig figs, 2 sig figs. That's also part of why I chose to put the decimal there. I mentioned this already, but since there's a coldest temperature possible, wouldn't it make sense to call that 0? Since we do, that's great, but that coldest temperature possible is negative 273 degrees Celsius. So if we want to go from Kelvin to Celsius, then our conversion is this. Like I said, this is rounded here, the 273. I was taught it's 273.15. I think technically it may round to 0.16, but I was taught 273.15. If you hear me say that at any point here, you understand where that came from. I'm totally fine with you using the 273 as this list here. So here they give us human body temperature. Human body temperature is 30 degrees Celsius. To be honest, when I see this, I think just add 273 to it. I almost said the 0.5 there, or 1.5 there. As a side note, if we write it out the way they have it, temperature in Kelvin is equal to temperature in Celsius plus 273. I like this because it's kind of how you're taught to do addition early on in elementary, and it works like that, and I get 310 Kelvin and 310. Since we have multiple choices here, that works. You'll notice all of these do have 3 sig figs. They're going to say that's because this is exact and that's exact, and they go to the ones place. It's essentially how I'd handle adding. I've mentioned before that I don't 100% agree with how your textbook handles sig figs when it comes to adding and subtracting. Anyway, a cold winter day, the temperature is negative 15 degrees Fahrenheit. What is that temperature in Celsius? So to go for temperature in Celsius from Fahrenheit, they told us that it's the temperature in Fahrenheit minus 32 divided by 1.8. And so then 15 minus 32 is going to be a negative, because remember when we subtract a negative is the same, or minus a positive number is the same thing as adding a negative. And so then that is a 47. And then if we take negative 47 and divide it by 1.8, we're going to end up with negative 26 degrees Celsius. This one here, 2 sig figs are significant out to the ones place. So this one here, 2 sig figs significant out to the ones place. Here's a table that compares some temperatures. You're more than welcome to take a look at it. Here is a medical example. Again, we used to say that human body temperature is 37 degrees Celsius, 98.6 degrees Fahrenheit. We now have it accepted that there is a range of temperatures. I mentioned when we covered measurement scales that this was not established all that well. It was a very limited data set that they had, and the myth stuck for a long while. But above this, you have hyper high thermia temperature. Hypothermia, you've probably heard of before, but hypothermia is cold, a low temperature, but there's a normal range for the human body. Hyperthermia, we usually get into calling this region here fever. Death can occur. Of course, there's exceptions for both of those in terms of there's a few, on occasion, rare people who survive really extreme temperatures. But it is not common, certainly not for the body temperature being at those extreme temperatures for long periods of time. So anyway, you can take a moment and read these if you want to, but let's go ahead and do this one here, one final practice. So we want the temperature in Fahrenheit from a temperature in Celsius, and so we know that we're going to multiply that by 1.8 and add 32 to it, and so then we're doing 34.8 times 1.8 plus 32, and punching that into a calculator, you'll get that it's 94.6 degrees Fahrenheit. And that finishes section 3.